Hello everyone. Today I'm going to talk about a research paper that broke the whole internet. So, in the year 2017, 8 researchers from Google published this paper, and the title only contained 6 words: Attention is all you need. And I'm not even exaggerating when I say this, that this paper actually created ChatGPT, DALL-E, and all other AIs that you have ever known in these past few years. And I get it, it's kind of complex to understand, but let's just try to understand it together. Shall we? Alright. So, before this paper even came out, if you wanted to use AI to translate languages, you would use something called RNNs, which also stands for Recurrent Neural Networks. And the problem with RNNs is that they process things sequentially. Like, imagine you are reading a statement word by word, then you can only move to the next word once you have already processed the current one. So, if I'm at word 100, I had to have processed word 1 through 99 every single time. And this created massive problems. Firstly, you just cannot parallelize anything. Like modern GPUs, which are insanely powerful, they can perform thousands of calculations all at once. But RNNs? It's like having supercomputers but are being only used as a calculators from 90s. The second issue was long-range dependencies just wiped out. If an information has to flow through word 1 to word 99 just in order to reach 100th word, by the time it gets there, it's already corrupted. It's like the telephone game that we used to play as kids. And the third, the training took forever. The best model before this, it took like 3 weeks to complete the training on powerful GPUs. So the researchers asked a very simple question. What if the distance didn't even matter? What if we could connect any 2 words in a single step? That's what the transformer does. Okay, so the core innovation is called attention. And honestly, the name fits so perfectly that it literally means paying attention to every part of the input. Here's the formula. Don't panic, I'll break it down for you. Alright, so QKV stands for query, key, and value. Let me give you an example. Say we have the sentence, the animal didn't cross the street because it was too tired. When we hit the word it, what does it refer to? The animal or the street? Your brain instantly tries to look back into the whole statement again and figures it out, right? That's exactly what attention does. So, Q is your query. That means, what am I looking for? K are your keys, which means, what's available to match against? And V are your values, which means the actual content once we find out what we are looking for. So when you do Q multiplied by K to the power T, that's just the dot product, which measures how similar the things are. The higher the score, it means, yeah, that's what we are looking for. Now, here's the clever bit. That square root of D underscore K in there. This paper had a footnote, which is quite very genius. While you're working with 512 dimensional vectors, the dot products can get really huge, like ranging from -22 to +22. And when you feed these numbers, which are being this large, to a softmax function, you'll get outputs like 0.9999 for one option and 0.00005 for all other options. So the gradients become so tiny that learning basically stops. So they just scaled it. Divide it by the square root of the dimensions while the variance remained at 1, gradients flowed properly, and everything worked out. Then the softmax function would turn these scores into probabilities and multiply by the values, and boom, you get attention. But wait, it gets better from here. Instead of doing this once, they did it 8 times. And each head can focus on different things. For example, one can work on grammar, another one can work on the meaning, another can work on handling the long range stuff, and the fourth one can work on like local context and so on. And because each head works on small dimensions, 512 divided by 8 gives us 64. That's the amount of computation cost, which is same as working with the same ones. So we have 8 different perspectives for the price of one. So let's build an actual transformer. Not this one either. Yep, this one. It has got 2 main parts, an encoder and a decoder. The encoder takes an input statement and turns it into a continuous representation. The decoder takes that and converts it into output, word by word. Both of them are made up of 6 layers stacked on top of each other, and each layer has got these subcomponents with attention. In encoder, every layer has multi-head attention where every word is looking at the every other word. Then there is a feed-forward network, and around each part, they added a residual connection and a layer normalization. The residual connection is just you add the input to the output. Sounds simpler, but it lets the gradients flow backward through the network very easily. Everything is in 512 dimensions, which matters for the residual connections to work. And the decoder is similar, but it has got 3 layers instead of 2. And here's the key difference. It uses masked attention. So now you want to ask, what is masked attention? During the training phase, you have the complete target sentence. But if the decoder knows its future words, it would just cheat and copy them. So also during the actual use, you don't know the future words, do you? Right. So masking sets the attention to -infinity for future positions. And after the softmax function is applied, it becomes 0. Each position can only see their previous positions. Now there is one crucial thing: positional encoding. Attention is completely order blind. Without positional info, the cat sat is identical to sat cat b, and they solve this with sine and cosine functions. Different frequencies for different dimensions. Higher frequencies encode nearby positions, while lower frequencies encode distance positions. The cool part is it is mathematically elegant. The model can learn its relative positions through simple linear calculations. And they tested it on positional encodings too, got the same results. But the sine cosine version can handle longer sequence than what it saw during the training phase. And oh, the feed-forward park. Just two linear layers with ReLU functions in between got them from 512 to 2048 and back down. So now you might want to ask, how to train this thing? They used WMT 2014 dataset, which contains 4.5 million sentence pairs in English to German. What about the hardware? 8 NVIDIA P100 GPUs for one machine. And what about the training time? 12 hours. Now you might wonder, is it too much? Well, the previous best model took 3 weeks. This is like 42 times speed up. They also used Adam Optimizer, which is pretty standard, but the learning rate schedule is quite interesting. For the first 4,000 steps, they increase the learning rate linearly. That's called warm-up. Then, after that, the decay following this inverse square root pattern. Now, you might want to ask, why warm-up? When everything is randomly initialized at the start, learning rate can cause chaos. So, gradually increasing it lets the things stabilize. They also use dropout, which is like randomly zeroing out 10% of activations, and label smoothing as well, where instead of saying that this answer is 100% correct, they distributed a bit of probability to other options. Makes this model less overconfident. For inference, they averaged the last 5 saved models and used beam search with a beam size of 4 and added a length of penalty to encourage longer translations. Okay, results time. Let's see what we get results for English to German translation. The previous best ensemble model got 26.36 BLEU, which stands for bilingual evaluation understudy. While the transformer, which has got just a single model, has got 28.4 BLEU. That's insane. Plus 2 BLEU is like, that's revolutionary in machine translation. And the training cost, well, it was like 7 times cheaper than the previous best. Can you tell me what is about the English to French one? Well, it was like 41.8 BLEU, which is like another state-of-the-art result. They also did these ablation studies where they tested out like different variations, which was like, how about we have one attention head? Doesn't work well. 8 heads? Perfect. 32 heads? Actually worse. That's too many. What about bigger models? Well, generally better. What about no dropout? You overfit. And here's the cool part. They tested it on like completely different task. English constituency parsing, where you are analyzing sentence structures with barely any task-specific tuning. They got 92.7 F1 score, beating almost everything. This proved that the whole architecture is actually a general purpose, not just at translation. So why does this work out so much better? Well, it comes down to 3 things. Number 1, the computational complexity. For typical sentences like 50 words and 512 dimensional embeddings, self-attention is about 10 times faster than recurrent neural networks. Number 2, parallelization. Well, self-attention is something which can do everything all at once. Recurrent neural networks have to go step by step. And number 3, which is a big one, is the path length. Any 2 words in a transformer can now communicate in one step. In RNN, well, the information has to go through every single position in between. So you can actually see this in the attention pattern now. Like here, the model connects the word making with the word difficult across the entire sentence. Or here, it figures it out that the word it's refers to the word's law. Different heads can learn different aspects, such as it could be syntax, semantics, dependencies. You can literally watch the entire model understanding in different language structure. So yeah, that's a transformer paper. Thanks for watching.